Okay, so next on my list, we discuss computing volumes of solids in free space by using my slicing technique. However, consider something a little bit different. I want you to consider a region bounded by the graph of some equation described as such. The x-axis between A and B. Rotate this two-dimensional region out the inkward in a three-dimensional space, one full rotation, and you're going to get an object in free space that kind of looks like this. Now, to compute such a volume of a solid of revolution, let's you and I, in our usual fashion from Calculus 1, construct a regular partition over the interval from A to B into n subintervals. Again, I'm sure I said this already. I use an adjective regular simply because each of the subintervals have the same length. Mathematically speaking, it's not required, but that's the way most of these textbooks set up these integrals, so I'm just going to go with that flow. Excuse me. Now, I want you to grab an arbitrary value of x in each of these ice subintervals. Sorry, I don't think I said that correctly. Grab an arbitrary value of x in each of these n subintervals. I'll just concentrate on the ice subinterval. How about this value of x? Use that value of x to go up to the curve, and the corresponding y value will determine the height of the proximity rectangle over the ice subinterval. Now what I want you to do is take that ice rectangle, not compute its area, but rotate it about the x-axis. And you're going to generate this little disk. And we're going to compute the volume of that disk. The volume of the disk is going to be the volume of essentially a right circular cylinder. And so the volume of that ice disk is simply going to compute it by looking at pi times this radius squared times its thickness, which is a small change in the x direction. And of course, the radius can be described by my function eval of x sub I asterisk. And now for me to take the sum of these v sub i's, then take the limit, then the volume can be described by an integral of the form here. If, however, I took a horizontal rectangle and rotated it about the y-axis, that's still the disk method, just about a different axis. The integral will look a bit different. Now, if you don't mind me saying, I'm just too lazy to remember all this, so I'll be honest with you. I just simply think of the volume in the end, using this new technique called the disk method, as an integral from A to B, a factor of pi in the grams position, which I'll pull out. And I just remember that I'm dealing with the area of a circle, which is pi times the radius squared, and that I multiply by the thickness. So in practice, if you merely remember this piece of cake, the variables and the quantities and expressions are all going to fall out nicely.